Dear students, welcome to this lecture of digital logic and system design. Today we are going to talk about the simplification of Boolean functions. By simplification, we mean minimization to a minimum number of product terms in SOP form or sum terms in POS form, with each product term in the case of the SOP and each sum term having the minimum number of variables in it. So this process of minimization will become more clear when we go through our later slides. Now this minimization can either be done using the Boolean postulates and theorems that we have seen in the previous lectures, or by Carnot's maps, or in short that is called as K-maps. That is also called Veitch diagram. So let us start discussing about the Carnot's maps. First of all, the simplest one is the two variable K-map, that is given in the form of, say, variables x and y. So I have the two variations of x over here, 0, 1, y over here. Now this term obviously is 0, 0 for both x, y being 0, 0. So this will be x dash, y dash. 0, 1 will be x dash, y. And 1, 0 would be x, y dash. And 1, 1 will be x, y. That is how we represent a two variable K-map. So we all know that this is 0, 0 corresponding to the min term m0. This is min term m1 because this is 0, 1. This is min term m2 because we're talking about m0, and this is m3 because it is 1, 1. Now suppose a function is given such that I just have m3 in it. So obviously this m3 can be written as xy, right? That is how we are going to write it. X because x is 1 and y because y is 1 as well. There is no other one here. That means there is no other min term in that function. So that is why it cannot be minimized, but can still be written using a two variable K-map. Let us take up this function in which I have the min terms. The function has got the sum of the min terms m1, m2 and m3. m1, m2, m3. Now we can combine the adjacent min terms. By adjacent I mean horizontally or vertically. I can combine them. The only thing that I cannot combine is diagonal elements. So we do not combine the diagonal elements. Now when we combine this horizontal ones that are adjacent to each other, and they will always be combined in powers of 2, like 2 to the power 0, which is 1, so no combination or just a single term. Then 2 to the power 1, or then 2 to the power 4 if all 4 are there. So they can be combined in powers of 2, in numbers which are powers of 2. So 2 to the power 1, which means I can combine these two terms together. When I combine these two terms, I see that y is varying 0 and 1. So y will get eliminated because it means I'm talking about y dash plus y. So whenever we have y dash plus y, that becomes 1, and 1 ANDed with anything will give me back the same thing. This x is not varying, so that is why this x will be there. So this will give me one of the product terms, plus the other product term will come from this vertical combination. In this vertical combination, x is varying 0, 1, so x will get eliminated and y will be there. So it will become x plus y. Suppose this one was not here but over here, then in that case x will remain the same because these two ones will combine, and since this one is not there but it is here, so this vertical combination will give me y bar. So in that case it will be x plus y bar. So in the case of two variable K-maps, the advantage of K-map may not be that obvious, but when we move on to like a three variable K-map, so when I say a three variable K-map, suppose those variables are x, y, z. Now this one is 0, 1 as we've seen in the previous case, but over here this one will have 0, 0, 0, 1, 1, 1 and 1, 0. They're not numbered as 0, 0, 0, 1, 1, 0, 1, 1 because in each successive element we just want to have the variation of a single place, of a single bit. So that is why we're going to number them in such a way that all the adjacent combinations, they vary in a single bit. And mind it, this is also cyclic, because 0 0 0 1 1 1 1 0, and when you go back to 0 0, there is again a variation of a single bit. So I can combine ones in such a way that the adjacent terms are combined. So correspondingly, this three variable K map can be written as M0, M1, M2, M3, because this is 1 0, this is 1 1. So M2, M3, M4, M5, M6, M7. That is how we are going to number them. Now suppose I am given a function x dash yz, and I want to minimize this function x dash yz plus x dash yz dash plus xy dash z dash plus xy dash z. So I can see that this is 0 1 1. X dash yz is 0 1 1, and 0 1 1 is 3. So I know that I'm talking about M3 plus x dash yz dash means 0 1 0, and 0 1 0 is 2. So this is min term 2. Xy dash z dash, so this is 1 0 0, so min term 4, because 1 0 0 is 4. Xy dash z is 1 0 1, which is M5. So basically this function in its canonical sum of product form can be written as summation of min term 2 3 4 5, as we have seen here. I've just sequenced them properly. So now I'm going to populate it in a three variable K map, because this is a three variable function that I want to minimize. So I'll have this generic three variable K map, and I'll place ones at all those places where M3 exists. So since there is no M0, so I'll keep it blank, or I may have kept it 0 also, but since I'm not going to combine 0 as yet, we'll do it later, we will see. So I'm just leaving it blank. Again, M1 is not there. You see, this is just 2. So what I'll do is I'll keep counting, and as and when they occur, I'll place a 1 there. So 0 1 2 3, 0 1 2 3. So 2 3 both will have 1 1. 4 5, they are ones, and 6 7 are not existent. So that is why they'll remain blank. So that is how I'll populate a three variable K map with the canonical sum of product form of the given function that needs to be minimized. Once this three variable K map is populated, then I'm going to look for adjacent ones. So I see that these two adjacent ones are there, which are varying in a single place. Since this variation is corresponding to x being 0, so I'll have x bar. The other variable in the product term will be y, and z will get eliminated. Why? Because this is 1 as well, right? So this is x dash y, because y is 1 whereas z is varying, so that gets eliminated, right? So I'll get my first product term. The second product term will come from this horizontal combination, wherein this is x now, right? Because x is 1. And over here I see that this is y dash. Z is varying, so z will get eliminated again. So this will be xy dash. So this is xy dash. So this pretty much completes all the ones in it. So this is the minimized function of the function that was given to me. So you see, so much minimization has occurred. There were 1 2 3 4 product terms. Now I have just 2 product terms, and within the product term there used to be 3 variables in each of those product terms, but here I've got 2 variables in each of the product terms. So quite a bit of minimization is obtained. So that will depend on the function, obviously. 3 variable K map. Let us take another example. Suppose I'm given 0 2 4 5 6 in its canonical form. So first I need to populate in a 3 variable K map. So this is a function of x, y, z. So 0 means a 1 here, and a 1 is not there, so I'll keep it blank. So 0 1 2 3, 2 is there, so 1 3 is not there, so that will be kept as blank. Then 4 5 are there, so 1 1 is here, and then 6 a 1 here, and 7 is not there in the given function, so that will be 0, right? So this is how I have populated my 3 variable K map with the given function in its with the function given in its canonical form. Now, how do I combine them? I look for the largest possible combination of adjacent ones in powers of 2, as I said in the beginning. And since this is cyclic also, I told you in the previous slide, this is cyclic also. So I can see that a combination, the largest possible combination is of 4 ones. And 4 is a power of 2. 2 to the power 2 is 4. So I'll combine all these together, right? So this will be a square containing 4 ones. So that is the largest possible here. So when I combine them, how can I write them? X is varying 0, 1 because this is a square. So X will get eliminated. Now in these two columns, I see that Y is varying, so Y gets eliminated, and Z is constant as 0, so that will be Z bar only. X gets eliminated, Y gets eliminated because both of them are varying. Z will be there, and that too it will be Z bar because this is 0. So my first product term is Z dash. Now I still have a 1 which is not covered in the previous combination of 4 ones. Now, if I write it alone, that will not be a minimization. So what I'll do is, since this is adjacent to this one, so I'll combine these two together. I can use a 1 multiple times because we know the theorem x plus x is x, right? So if it is helping me in minimization, so I may use this one twice or thrice maybe, or even more times if it is going to give me a better minimization. So I'll combine these two. When I combine these two, I get x because x is constant as 1, and z is varying. So z will get eliminated, y dash because y is 0. So x y dash. So for the canonical sum of product form of this function, the minimized function would be z dash plus x y dash. Let us take another example. Suppose I'm given a function which is not in its canonical sum of product form. It is not like this. How can I say that this is not in canonical sum of product form? Because each product term is not having all three variables. Like this one is not having b, this one is not having c, this one is having all a, b, c. This is fine. This is not having a. So I need to first convert it into the canonical form, because only then I will be able to populate it in the K-map. So how do I do that? One easiest method is to use the distributive property. Later, we will see that we can, in fact, convert it into the canonical sum of product form using the K-map itself. That we will see later. Let us do the simpler thing right now. A dash C, let me AND it with B plus B dash. Because B plus B dash is 1. So anything ANDed with 1 will give me back A dash C. So this is not going to hurt me if I do the ANDing with B plus B dash. Similarly, A dash B can be ANDed with C plus C dash. Again, that will be 1, and this is not going to make any difference. Any error as far as the function is concerned. But this will make a difference, as we'll see later. Now, this I'm not going to do anything because it contains the three variables already. This doesn't contain the three variables. The one which is missing is A. So what I'll do is I'll AND it with A plus A dash dot BC. So now I use the distributive property. When I use the distributive property, A dash Z, A dash BC. Let me write it, A dash BC plus A dash B dash C. I can use it because that is commutative. So what I can do is, let me put it in the proper sequence. A dash B dash C. Over here it will be A dash BC plus A dash BC dash. A dash BC plus A dash BC dash. Plus this will be copied as it is, AB dash C. Now this will be ABC and this will be A dash BC. So I see here that A dash BC is being repeated 3 times, and I know that x plus x is x. So I can cancel them out, right? So it will basically be x plus x plus x, that will still remain x, right? Because x plus x is x, so x plus x plus x will be x plus x, that will be x only, right? So I can cancel them out. That is why you see that this has been struck off. Now let me write them in the proper sequence. First of all, let me write A dash BC B dash this one, A dash B dash C plus A dash B C dash, this one comes here, then A dash B C, and then A dash B C has come here, and then A B dash C, and then A B C. Now what is this? This is 0, 0, 1, which is 1. So M1. A dash BC dash, so this is 0, 1, 0, M2. This is 0, 1, 1, so M3. This is 1, 0, 1, so M5, and this is 1, 1, 1, so M7. So I have got the canonical sum of product form for the given function, right? And I'm trying to minimize this function, so it is required that I must first convert it into the canonical sum of product form, and then I can populate my K-map accordingly. So this is summation 1, 2, 3, 5, 7. So let me count it. 0, that will be kept blank because there is no 0 there. 1, 2, 3, all ones here. 1, 2, 3 are existing. 4 is not there, so a blank. 5, a 1 here because that is existing here. And 6 will be a blank. 7 will be a 1 because there is no 6 and there is 1, 7 there, right? So that is how I can populate. Now I have to combine the functions and minimize them. So I must be looking for the largest possible combination of adjacent ones in powers of 2, the numbers in being in power of 2. So I see that this can be this square. When I use this square, the largest possible, then you know these two get eliminated because they are varying, and similarly B will also be eliminated. Only C remains, and that will be C. It's 2 form because it is 1. So I've got the first product term as C. Now this one remains, so I'll combine these two now using this once twice. As I said in the previous example, when I use this, this is A dash B, and C gets eliminated. So A dash B is my answer, right? So this is how I've given you a few examples. How can a 3 variable K-map be used for minimizing a function with 3 variables? Now a 4 variable K-map, 2 variables on this side and 2 variables on this side. Let me also tell you one thing, that it is not necessary that the 3 variable K-map is horizontal only. I can have a vertical 3 variable K-map also. In that case, I'll have 2 variables here, xy here. xy 0, 0, 0, 1, 1, 1, 1, 0. And z will just have 0, 1. Still, I have to combine using the same way. So, but in the case of 2 variable K-map, and now in the case of 4 variable K-map, they can only have this particular form. So wx2 variables on this side, 0, 0, 0, 1, 1, 1, 1, 0. The combination will remain like 1, 1, 1, 0. The sequence will be this. Similarly here, 0, 0, 0, 1, 1, 1, 1, 0. So that the adjacent columns or the adjacent rows, they vary in a single bit. Only then they can be combined and minimized, right? Let us take this example. Suppose I am given a function of 4 variables having these minterms. I need to populate it. Yes, let me go back and see how will the minterms be counted now. This is 0, 1, 2, 3 because this is 0, 0, 0, 0, 0, 0, 0, 1. Then 0, 0, 1, 0 is here and 0, 0, 1, 1 is here. So this is 1, 2, 3, 4. M0, M1, M2, M3. So 0, 1, 2, 3, 4, 5, 6, 7, and then 8, 9, 10, 11, 12, 13, 14, 15, right? This is 1, 1, 1, 1, so that will be 15. This is 1, 0, 0, so 8 will come here, right? So I must know the numbering. When I am sequencing it like this, I must know the numbering. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So using this sequence, let me populate my K-map with the given function to be minimized. So 0, 1, 2, 3 is a blank. So 0, 1, 2, all 3 were there. So I place 1 here, 1, 1, 1 at all these 3 places, and 3 is blank. Now 4, 5, 6. So 4, 5, 6, 7 remains blank because it is not existing. Then 8, 9, 8, 9 are there. Now 10, 11 are not there, so they are kept as blank. 12, 13, 14. So 12, 13, and 14. 15 is again a blank. So all the min terms, they are denoted by ones in the appropriate place. The place being decided by 1, 2, 3, 4, 5, 6, 7, 8, 9, sorry, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that is how you populate a 4 variable K-map. After that, you have to look for the largest possible combination. So you see, The largest possible combinations of ones is this one, and it contains 8 ones, and 8 is a power of 2, so I can combine it. I may not have combined 6. I may not have combined 6, right? Suppose these two ones were not there, or only one of them was there, so I could not have combined 6 because 6 is not a power of 2. So it has to be combined, leaving a single bit or two bits together, two adjacent bits together, or 4 bits or 8 bits or 16 bits or 32 bits, as the case may be. So it has to be in powers of 2. So this is the largest. So look for the largest possible combinations of ones where the number is in powers of 2. Now when I use this one, so I see that all wx are varying, because 0, 0, 0, 1, 1, 1. So both w and x will get eliminated. Over here, since these are the two columns, z will get eliminated and this will be y bar. So what I'll get out of all this combination will simply be y bar. So you see, I get y dash. So all these ones are covered. Now let me come to this one. See, when I come to this one, I see that this is adjacent to this one. So I must look for the largest possible combination, and they are cyclic also. So the largest possible combination will be like this. 4 ones together. I told you I cannot combine 6 ones. If I could have combined 6, then I would have taken these 2 and these 4. But I told you that we can combine only in powers of 2. So this one will be combined with this one. This being treated as a cyclic or a foldable K-map. So when I combine these 4, you see x gets eliminated because that is varying, and this is w bar or w dash. Again over here in these two columns, so I place a w dash here. In these two columns, I see that this is z dash and y gets eliminated. So w dash z dash. Y dash is what I got from this one, and from this one I got w dash z dash. Still this one remains. I have to cover all ones. So but in order to cover this one, I see that this should also be combined with 4 ones in order to have the largest possible combination of ones in powers of 2. So if I take it alone, I'll have a product term which will have 4 variables. If I combine with these two, then I'll have a product term with 3 variables. But if I combine all 4, this product term is going to give me just 2 variables. That is what we discussed in the very beginning. The first slide I said, what do we mean by minimization? So when I combine these 4, you see w gets eliminated, I get x. So I place that x here. In these two, I see again that it is z dash. Y gets eliminated. Why z dash? Because z is 0. So x z dash. So this is the minimized form of the given 4 variable canonical sum of product form function, right? So this will be the minimized form. If I had not minimized it, I would have got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 product terms, and each product term having 4 variables in all the product terms. So that would have been a huge function, right? Later we will see when we implement that this is going to solve or make it easier. Our implementation in the logic diagram will also be easier, but we will see that later. So that is how 4 variable K-map works. Another example. Now over here you see I'm given the function which is not in its canonical form. By this time you have practiced enough. So I hope that you will be able to convert it into the canonical sum of product form without resorting to distributive property. If you resort to distributive property, well and fine. Suppose I had to resort to distributive property, what I'll do, I'll combine. You see, I can see that there are 4 variables. So I'll have to do a dash, b dash, c dash, and d plus d dash. Similarly, over here it will be a plus a dash within brackets dot b dash c d dash. Then this doesn't require any change because it already has 4 variables. And again over here I'll have to AND it with d plus d dash in bracket. So then only I would be able to get the canonical sum of product form when I open those brackets using this distributive property. But let us try doing it directly in the K-map. You see a dash, b dash, c dash. What does it mean? 0, 0, 0. So you see, I'm 0, 0, both of them being 0, that means I'm talking about this row. And C dash. So C dash means this and, sorry, not this. C dash means this and this. So A dash, B dash, C dash can be represented by these two ones, right? Because A dash, B dash, C dash. So that is what we can learn by practice. So A dash, B dash, C dash is going to give me these two ones. B dash, C D dash. Similarly, how can you populate them? B dash, C D dash. So C D dash means C D dash means these, sorry, this one. C D dash means this one. C D dash, because D is 0. And then B dash. So let us look for B dash. B dash will be this row and this row. So what I can do is I can place a 1 here and a 1 here. The one at these two places will correspondingly be B dash, C D dash. So this term, product term, which is not in its canonical sum of product form. So this is giving me these two ones, and the other product term is giving me this one as well as this one. Now A dash, B, C, D dash will be a single one, right? And let us look for 0, 1, 1, 0. 0, 1, 1, 0. So 0, 1, 1, 0. So this one is corresponding to A dash, B, C, D dash, a single one. Now again AB dash, C dash. So let us look for AB dash. AB dash is here, right? AB dash. So I'm talking about this row. C dash. Where all do we get C dash? We get C dash here and here. So these two ones put together will be corresponding to A, B dash, C dash. So A dash, B dash, C dash will give me these two ones. B dash, C, D dash is going to give me this one and this one. A dash, B, C, D dash is going to give me this one, right? Yes. And A, B dash, C dash is going to give me these two ones. So that is how our 4 variable K-map has directly been populated without resorting to the conversion into the canonical sum of product. Now once it is populated, let us try to minimize it by looking at the largest possible combination of ones. So we see that largest possible combination of ones is these 4 ones put together. Again, this is cyclic like this, foldable like this, because 0, 0, 0, 1, 1, 1, 1, 0 and 1, 0, 0, 0 are again varying. Now let me also connect. Remember gray code that we talked about, reflected code that we talked. This is one of the applications of reflected code. This I am writing in the reflected code or the gray code. Each successive number or each successive row and column is varying in just a single bit. Then only it can be combined, right? So the largest possible combination is 1, 1 and this one, because they are adjacent. They will be treated as adjacent rows. There is no other larger possible, like I do not have a combination of 8 ones in adjacent rows or columns. So the largest possible is 4. Now when I combine them, what do I get? A gets eliminated, I get B dash, right? So I wrote B dash. Again over here C dash remains and D gets eliminated. Hold on, yes. So it will be B dash, B dash and C dash. So it will be this term, B dash, C dash. B dash, C dash will be the combination of these 4 ones. So these 4 ones are covered. Again, you look at the interesting part of it. I have ones at the 4 corners, right? So since this is foldable like this and this is foldable like this, both ways it is foldable. So I can combine the corner terms also. I can combine these 4 ones at the corners, right? Because this is foldable like this and this is foldable like this. When I combine the corner terms, what do I get? A gets eliminated, B bar, right? So I get B bar, and then in these 2 columns D dash will remain, C gets eliminated. So I'll get B dash, D dash. So one combination of 4 ones is giving me B dash, C dash. The other combination of 4 ones is going to give me B dash, D dash. So you see, What all ones have been covered? These four ones and the column ones. Now this one only remains. Rest of them they have been covered, right? In order to write this one, I can see that this can be combined by counting this one twice, because that will give me a better minimization, and there is no other way that I can combine this one, right? Had there been a one here, it could have been combined, but there's no one there, so I'll combine with this one only. When I combine, I see that A dash, B gets eliminated, C D dash. So A dash, C D dash. So this is how this can be combined, right? So I think I'll stop here, because you know, a new concept has been introduced today, and this new concept needs a lot of practice. So try getting functions of your own and try practicing using minimization using k-maps for two variables, for three variables, four variables. Take random functions, in sum of product form, canonical sum of product form, and then take any intermediate form. This particular form, I'll call it intermediate form, because this is neither canonical sum of product nor the minimal. You see, minimal is this one, and this is not canonical either. So this is some intermediate form. For the intermediate form, I need to first convert it into the canonical sum of product form. That I can do using distributive property, or I can do it if I have enough practice with k-maps. So I can do it directly also. So we'll stop here, and then we'll continue in the next lecture from here on.